Okay. Hi, everybody. Thanks. Okay, but I have a... I shot a lot,
but you are being recorded.
Ah, sorry.
So you need to use this one.
So I'm nervous now.
Yeah.
Okay. Hi, everybody. Thanks, Roberto, for the invitation. It's a pleasure for me to be here. This presenting our work. This is a collaboration with Fernando Peruani from France and Benjamin Marcolongo. He's making his PhD with me in Córdoba. And he will present a poster tomorrow, and I hope that everybody asks him a lot of questions. Please. I will pass the introductions quite fast because I think that everybody knows what I'm speaking of. What I will consider is diseases that are transmitted not through a vector, but from direct contact, from one individual to another individual. These are some examples, from high to low infectivity, or if you prefer, from low to high level of intimacy needed to transmit the disease. And what we are interested in, or what we start thinking, is how these diseases, or the epidemiology of these diseases, are modified in big cities where there is a lot of people that have contacts, but just a brief period of time, and they have almost no contact at all, and they move, and it's crowded. And I, for example, live in a very small town that 20,000 people, and there the people is quieter, so but at the contrary, when you interact with someone in a store just for the first time buying something, they love to talk, and the interaction is long, and everything is completely different of a big city like Córdoba that has more than 1 million persons, where everything is fast, everybody wants to be in another place, and then they are rushing everything. So our question was how the interaction time of the people and the mobility, thinking on how many interactions. Mobility, we are not thinking on how fast we are moving, just how many interactions we have in a day, for example, how these two parameters modify the evolution of an epidemic of this kind of disease. These are another examples that are quite famous in the last year, but, we can extend our work to other areas like cell activation, for example, of some gene, mobile phone dynamics, considering Bluetooth. There are some viruses that are going from one cell to another cell phone to another cell phone via the Bluetooth connection. Rumor spreading or opinion formation, considering sociology, in which one information is passing from one to another, and that is completely different in one big city than from a small city. But when we start to work on this, we were thinking on mobility, in terms of bacterial. I don't understand why it is not moving. Okay. And you can see 3 different kinds of bacterial movement there. One is quite ballistic. They move in a certain direction and change the direction just a few. And other, like this one here, that moves quite random, changing direction all the time. So if we think on people I didn't want the music, but it's appeared all the time. You can see that there are people moving in a straight direction, just colliding with another, but like cells moving ballistically. And here you have another persons that are moving from one table to another table, chatting with other persons and kind of diffusing. So then again, we will make some analysis considering the movement of bacteria, thinking on people. These are previous works that try to understand how the dispersal of a disease is modified by certain parameters, but none of them has a direct or include a direct analysis of the interaction time of between two agents. Maybe it's hidden inside some of the parameters, but not in a direct way. And then, okay, this will be fast. We will consider a population of susceptible, infected, and recovered or resistant individuals, like everybody knows is the SIRS model of Kerman and McKendrick. And then we have in this what we call the mean field model, that we have these three populations, and you can pass from one to another with certain probability, and the only one that you need the contact is to pass from the susceptible to the infected, as everybody knows. We are considering a closed system, that is, the total population is constant. These are typical Kerman-McKendrick equations, and these are the steady states. We have two steady states, the disease-free or endemic state, and the stability is from one to the other steady state is given by a parameter, or by these parameters, if the infectivity is higher or lower, these parameters that depend on the size of the population and the infective time. Okay, going back to our model, we start working in a numerical model. We consider a two-dimensional area. In that area, we have disks that are the individuals. These individuals will move with in a certain direction, and you have a lot of here, and they can interact. When they interact, they start to overlap a little bit, and when they overlap, appears a force that tries to divide them, no? And then when they start to interact, what they do is like pushing one to the other until they separate. Then we have a contact, that is contact between these two agents for a finite period of time, and in this period of time is when the infection can occur. The speed of this agent will be a constant, and again, think on the speed as a parameter of how many contacts they will have. If the speed is very high, they will have many contacts per unit of time. If the speed is very slow, they will have just a few. And from time to time, this speed or this direction of the speed will change with a probability that is have a characteristic time that I call tau rotation, and it says the mean time of changing direction. So they will change the direction of movement in average tau rotation. With this in mind, we perform simulations, and you see that we start with a population that is, everybody is susceptible, and suddenly the outbreak occurs. There is a lot of persons infected, but they recover and end in a steady state with a certain noise. These are a simulation, typical simulation. And you see that the red dots are the infective, and you see that suddenly everything is red, and then everything is green, and at the end everything is mixed. But quite fast in this simulation, the population is mixed. We consider in that simulation that the speed is fast compared with the size of the population. Then we wanted to perform some analytical results, to have some analytical results, and then we use kinetic theory for a system that has a low density and then if we consider a mean collision time omega, we can find that the collision probability with an infected is given by this. Just considering that there is an agent that is moving in a straight line and collide with another doing the same thing. With this collision probability, and it's also depending on the transmission time needed for the disease to be transmitted. And with this, we compute the infection parameter, the effectivity, and with this, we had the susceptible steady state given by that. So we make the simulations, and we compare with this. Before doing that, what I need, is this parameter that is the mean collision time. That is something that I don't have. So with our simulations, we start to compute how, in average, they collide. We found that the distribution probability of the collision time are exponential. Then we can compute from them the mean collision time, and found that the mean collision time follows a line that is in an exponential in a log-log graphic. It's inverse, the inverse of the speed, and then we found that the mean collision time is given by this relation, and we can adjust the parameters. But this parameter zeta is very near to 1. With that, now we compare the simulation with our model, and we found that these adjust quite well. There are some problems at the end from very small transmission time, but I want to emphasize here that the disease disappears when the transmission time needed for the disease to be transmitted is larger than the mean collision time. That is something that more or less one can expect. If the disease needs a lot of time to be transmitted, and the mean collision time is smaller than this, the mean collision time is smaller than the transmission needed for the disease, then the disease will disappear. Next, we compare the simulation, changing or varying the size of the box, of the area. What is more or less to say how change the epidemiology with the density of the people. So when the size is very small, we have a very crowded situation. If the size is very high, the density is small. And we found that the disease disappears for a certain value of the density, let's say. If the density is very small, then the disease will disappear. Of course, if we need to move to reach another agent, and the other agent or the other individual is far away from me, then I will not reach fast enough the other individuals to infect him, and then the disease will disappear. if you see here, our mean field approach doesn't fit very well. When the size is high, yes, but when the density is very low, there is a difference, let's say, and we think that that is for multiple collisions. And then at the end, we change the speed, that is how many contacts an individual has per unit time. And we see that, of course, if the speed is very low, so there are not so many contacts, the disease will disappear. There is then a threshold here for the velocity equal to this, that the endemic state appears, and it depends inversely linear with the speed until a second threshold. And in this threshold, the outcome of the disease will depend of a parameter that, remember this theta, that appears there, and then it says that depending on how the contacts are, and how the contacts depend on the speed, it will be the outcome of the disease if there are many contacts. In our model, with a specific potential, soft core potential, these are the simulations, and the continuous line is with the parameter that we adjust from the from the collision times. But nevertheless, if we have situations that the collision time or the interaction times depends differently with the speed, or saying in other words, how many connections, how many contacts are, then we can have a different situation. Thinking on that, we change our parameters to reproduce this, and for example, is the transmission time needed for the disease to transmit the disease is 0, for example, so all the contacts will transmit the disease. Here, this goes to infinity, and then all this third regime never appears, and is what we found. And if we change, we make some simulation changing, how can I say, we make another potential and change the interaction time in a way that it's increased with speed. We found what we saw in the theory, that if after this threshold, the disease or the number of susceptible will increase, and there will be a decrease in the cases of infections. But all the previous analysis was performed considering that the interaction were ballistic. So we have one individual that collides with another individual that are moving in a straight line without changing the direction of movement.
What if a mean field,
sorry?
What if a mean field solution is the master equation for those probabilities? What's
the previous?
The mean field.
The mean field is the solution of the equations, the differential equation.
Yeah, the master equation.
Yeah. Considering parameters that are constant. And then here, then what happens if we move from this situation to another situation in which an agent, before colliding, is changing directions a lot of time, so it will need more time to reach the other agent, and we call this situation the diffusive. If we think about the two characteristic length, the distance between two agents, the mean distance between two agents, or the mean distance that an agent runs between two tumbles, let's say the two changes of direction. This rate we characterize the movement from diffusive or ballistic. And what we found changing the rotational time is this. We can have, we can eliminate the disease if the movement start to be more diffusive. That is, if I don't move long distance, but I move just in my neighbor. Just thinking of the previous work is that if the people is moving in a certain area and not moving so far away, then the disease sooner or later will disappear. On the contrary, if they are interacting a lot with a lot of people and moving a lot in that area, we reach to what we call before the mean field approach, and the population, the susceptible population, is inverse proportional with the speed. And if you see here the simulation, from that first red dots, it'll increase in that area first, and it's growing the red area outside till they reach almost all the simulation, but then the green dots appears, and at the end, of course, we have the same or a similar situation and the previous simulation. What happened if we previously, in a previous analysis, the key parameter was the mean collision time. What happened with the mean collision time now? We make, and again, the measures and the simulations. This is the case that we had before, that if the speed is high, then the mean collision time is low. And what we see is that it's almost constant, the mean collision time, till they reach a linear proportional between the mean collision time and the rotational time. Because if we had two agents colliding and they start to collide and one of them change the direction, then the collisions disappear. It's like I start talking to someone of you and suddenly I change my mind and I start to speak with another. So, sorry. Oh, here. Then the mean collision time starts to be proportional to the rotational time, to the time that I am talking to you before changing my mind and start talking in another direction. And that is the reason that it changed the populations. Here again is the number of susceptibles, the mean number of susceptibles as a function of the speed. And we say that this is the previous analysis for a very long, this parameter is the rotational time. For a very long rotational time, it goes quite well. But when we start to reduce, now we change and we have another line behavior, linear behavior in a log-log picture that corresponds to diffusive behavior. And from the analysis similar to the previous one, considering diffusion, what we found is that the susceptible population must be proportional to the minus square of the speed over the rotational time, and that follows exactly this line. It's what we call the diffusive approximation. And if we compute the susceptible population, the mean susceptible population, as a function of the rotational time, we say that for rotational times very long, again, we have the previous situation that depends with the speed. The higher the speed, the lower the susceptible population. But when we start to decrease the rotational time, again, we have this linear behavior that is given by the rotational, the diffusive approach, let's say. And to the end, and just making a spoiler, let's say, of the work of Benjamin, we ask ourselves what happened in our previous analysis if we introduce a vaccination program, that is, a population of people that is vaccinated. Because in Argentina, there is a growing population, growing number of groups that say that the vaccines are dangerous, and you have some community that is vaccinated, so there is no need to have something dangerous just because there is no need. And I found that situation in Spain, Argentina, and here in Brazil is also the same. There is a lot of people that are avoiding vaccines. I will not tell you the whole story. I left this to Benjamin. But just want to tell you that we found that the vaccination program has to be very, very large to cope or to be productive, let's say, in big cities. This is the number of vaccinated individuals, the percent of the vaccinated individuals needed to eliminate the disease in cities with this density, and these are some examples of density. This number is in inhabitants per square meter. You see that with just an example, we consider a disease, an example disease. You need more than 90% of the population vaccinated to eliminate a disease in those cities, in the big cities, I say. And I'm not speaking cities big as New York, Manila, that is like there. So, okay, this is for to the end. I ask you, please, to go to Benjamin poster and ask him for the details. Okay, this was all. Thank you very much.
Thank you, Gustavo.
Sí. Yes.
So, questions? Everybody's already tired.
There's something funny about your last slide. Is São Paulo density 10 times smaller than New York?
Yes, it's strange for me, but I took this number from Wikipedia and says that downtown São Paulo...
It's probably equal New York, but I think it's not a uniform distribution, right? So it becomes...
Completely, yes. These numbers, I took them from Wikipedia, and it's density downtown.
Also from your plots, I was trying to get the equations, because when you go... when they converge, because you have too many collisions. If you're in a situation where you have too many collisions, the diffusive and the other one should agree at some point, right? And that was trying to...
Let me see.
Is that the regime?
Here?
No, before, when you're here, or the one before here, right? So basically, if you assume that you take too many collisions to get infect, if the infection is small, then you can have an effect diffusion coefficient, right? In a sense that multiple collisions will give you a...
Yes, if the density is very, very high, I don't understand very well your question, but if the density is very high...
If you want to get infected, you have to have many collisions. You're going to have, in the end, an effective diffusion coefficient, because...
Yes.
So the equation should be the same.
No, but wait a minute. When you collide, you don't change your direction of movement. When you collide, your direction of movement is fixed. You want to go in that direction, and suddenly someone appears in the middle. So you start to collide with them until one with this force, I will show you, I think this, no, here. The active force, is the speed that you have, is constant. You don't change it. So, but
change the direction.
So,
But you're going to change the direction.
no, you don't change the direction. You
just
change the
go
direction,
over?
sorry, you change the direction between long times in the diffusive movement. But if you are in the ballistic situation, you don't have change of direction. You want to go in center direction, and suddenly you collide with another, some obstacle, and you start to try to push it, but so, for example, let's say this one. It's going in this direction, but this one appears, and then a force moves you away from the obstacle, but you want to go in that direction, and then you will, your speed will be in this direction for this time step, but in the next time step, when you end the interaction,
So you're not treating your collisions like billiard balls?
No.
Okay.
No, they don't go, well, yes, a little bit, yes. I'm sorry, yes. But because there is an interaction and they push away till they end the collision, and both of them continue with the previous speed. Yes, there's a potential. I didn't put it here, but it's a potential. And soft core potential. I have it somewhere but yes, it's a potential, soft core potential.
Regulates in some way the time they are overlapping?
No, the potential regulates how.
What means overlapping?
No, the overlapping, for example, if we put two of them collide just from front to front, they will stuck there, overlapping a little bit because a force appears trying to separate them. If you put just one above the other, and then they will start to this situation till this force that appears push them away. So the overlap, the potential of the size of the potential of the overlapping says how far the interaction will put you away, but if we make that, we have to start considering time steps smaller, and then the overlapping, this high overlapping will never occur. It's always a very small overlapping that the only thing that do is to keep physical contact of both agents during a certain period of time. And the only thing that they do is to avoid each other until it's like turning two wheels till one of them is free. And depends a little bit of the size of the potential, but not so much. It depends because I don't like to put it here because it depends of the numerical analysis of the problem and not on the problem per se.
More questions?
One question. Do you have two models? The diffuse model and the ballistic model. What about a mixed model?
No.
Sometimes it's diffuse
it's
and
the
has
same
a probability to ballistic to another region.
It's the same model, but with two different analyses to get some analytical results. So our idea was to, with the first analytical model, we have some results. This one, that was very interesting for us. And then we said, okay, but we are considering here just a very not so crowded situation. Everything is it's almost ballistic. What happens if we have something that is more diffusive with a higher population? And then we get the other analytical model that, and we compare that with the numerical one. The numerical model is always the same. The only change in the numerical model is this one, in which we change the potential. The interaction potential is completely different, and the higher you interact, the higher the interaction ends. So they push you away harder than the previous one if the speed is higher. And it don't depend of how much they overlap, but only of the speed. Okay.
So, thank you again, Gustavo. Tomorrow, we start at 10, right?
Okay.
Thank you very much for...
Oh, thank you for...